We are the RoboFridge group. My name is Kaylee Schmidt. I was born and raised in Salem, and I'm a graduating senior here at OSU.
My name is Sean Hewitt from Lincoln City, Oregon, and I have a year left here at Oregon State.
My name is Chris Tennant. I'm from Portland, Oregon, and I'm a graduating senior this coming fall, and I'll be going on to graduate studies.
I'm Alejandro Nunez. I'm from Mexico City. I'm also a graduating senior, and I'm going to be working on software for hospitals after school. This is our project. It's a can launching fridge. It operates via RF, so the user can activate it at any time with a remote control. Once he activates it, it'll use a sonar to determine the distance between the user and the fridge. After that, the user can set up a personalized distance using an LED display, which will indicate the distance. Pressing the launching button again will load a can into the barrel, reload for another launching in the future, and within a minute fire at the user, providing an audio alarm so that no one will be disturbed.
This is our top level block diagram. As you can see, the gray blocks correspond to mechanical components, the green block corresponds to our code, and the white blocks correspond to electrical components and sensors. This is a mechatronics project, which can be seen by the fact that we have a controller which is programmed and then controls the whole system. The controller receives input from the user and through various sensors installed on the project, and gives output mainly in the form of communications with the user and mechanical energy through motors and the air cannon.
Our RoboFridge has a very user-friendly interface. It is remote controlled by this 5-button key fob. 2 of the buttons turn the fridge left and right, 2 buttons increase and decrease the launch distance, and 1 button initiates the launch. When the user presses a button, the corresponding data line on the RF board, which is located on the top of our fridge, will go high. This signal is seen as a logic high by the microcontroller, which will then carry out the desired function. When the launch button is pressed for the first time, this sonar sensor will emit a sonar signal, which will bounce off the user and return to the sensor. The sensor calculates the time of flight of the sonar signal and sends it to the microcontroller. The microcontroller will then compute the launch distance. The launch distance will be displayed right here on this LED board. Each LED represents a foot in our range of 5 to 15 feet. When the launch button is pressed again, the launch sequence will be activated.
Okay, so here we're just gonna show that the distance indicator can be changed by using the RF. So first we trigger it, and it went to 5 feet just because there's an object at 5 feet from our feet.
9 feet.
9. So now by pressing this button, I can increase it, and I can keep doing that. All the way to the maximum, and by pressing this lower button I can do just the opposite. And yeah, that shows the RF functionality with the distance indicator.
The microcontroller that we chose for this project was the ATmega 128. We chose it because we've had experience using it in previous classes, as well as the fact that we had several of them, so it was the most cost-efficient solution. The code of the controller is divided into 2 sections. One in the main loop, which has all the user interface stuff, So that would be the sonar and receiving the pulse from it, the RF, the LED display and other LEDs, and the pop switch. The other section of it is in interrupt, which trigger every 1/28th of a second, which allows us for accurate timing of controlling the motors for the barrel and the loading and reloading of cans, as well as turning the air compressors for the appropriate amount of time to fill them to the right PSI.
This is our can storage system. The first can placed in the system is placed on this sensor. The successive cans are placed here and then up stacking through the vertical assembly. The assembly can hold up to 10 cans at one point in time. When the specific point is reached in the firing sequence, this motor will fire, removing a plastic stopper from underneath the door, and the weight of the can that's sitting on the sensor will cause that can to fall into the barrel. Next, the door will raise, like so, hitting that wooden support there, and causing successive cans to fall into the door. Then the door will lower, plastic stopper will be replaced, and the system will be ready to drop the next can. A sensor has been installed on the door such that cans can only be fired, or the system will only begin firing if a can is present. To supply our system, we use 4 ATX power supplies, and we have 2 sets of 2 power supplies in parallel. That's to reach the current necessary for our rotational motors.
This is the air cannon overview. When the machine is first turned on, it fills up to a PSI required for the minimum 5-foot distance. This takes approximately a minute, a little bit less than. It fills using air pumps into a 4-inch PVC pipe that is about 1 foot long. It then is controlled using an air valve that is hooked up to a relay, which is controlled by the microcontroller. When input is given from the user and the distance is found, the air chamber is filled according to what the microcontroller has read from the sonar. It then also raises the cannon barrel to receive the can. When it does so, this bumper right here helps align the can to fall down into the barrel. At the same time, if necessary, the air pumps will be running. So several things are happening all at the same time. When the can has fallen into the barrel will be relowered using the motor in the back that raised it initially. When it gets to the bottom and the PSI has reached its desired amount, the cannon valve will open, expelling the air that has been compressed with such force that it will launch the can at the desired distance.
This is to show that the fridge is rotating using RF. Here's the first direction. And here's the second direction.
One of the major challenges we faced on this project was the rotational base. Due to budget constraints, we weren't able to get a really expensive motor with a lot of torque. So the system required more torque than the motors we had could handle, and the brackets themselves that we purchased were not able to handle the torque and were bent and twisted, allowing give to happen, which caused the system to not work consistently.
Another of the major problems that we encountered was getting cans to come out of can storage directly into the barrel. That resulted in us installing this net just in case a can were to miss, and installing this rubber stopper. And the stopper functions by hitting the can early on as the can falls, and then the can will rotate into position to fall into the barrel. And this implementation did succeed.
So the biggest tip that we have is to choose your team according to the project that you're going to be doing, or to choose your project according to the team that you have. because you have to be able to look at all the different aspects of your project, the electrical, the computer science, and the mechanical of it, and make sure that your team will be able to handle it.
Overall, we're very satisfied with the way our project turned out. We met all of our engineering requirements, and we were able to successfully launch cans all day at the Engineering Expo.